determine the stability factor SVBE and change in IC, SVBE and change in IC from 25 degrees Celsius to 100 degrees Celsius. Okay, 100 degrees Celsius for the transistor with VBE at 25 degrees Celsius is equal to 0.65 volts and VBE at 100 degrees Celsius is equal to 0.48 volts. Okay, all right. So there are two temperatures, 25 degrees Celsius and 100 degrees Celsius. You know that VBE depends on the temperature value. Okay, as the temperature starts increasing, VBE starts reducing. So at 25 degrees Celsius, probably the room temperature, it is at 0.65 volts level. And when the VBE is increased to 100 degrees Celsius, the voltage has dropped to 0.48 volts. Okay, for the following biasing arrangement. So SVBE and change in IC for this particular circuit condition, you need to do it for the following arrangements. Fixed bias, FB fixed bias with RB is equal to 270 kilo ohm and beta is equal to 120. Second, emitter bias. Okay, I'll use the short form. EB means emitter bias with RB is equal to 39 kilo ohm, RE is equal to 1.2 kilo ohm, and beta is equal to 120. Okay. Third one, voltage divider bias with R1 is equal to 39 kilo, R2 is equal to 10 kilo. This is 39 kilo ohm, okay, not 3.9 kilo, what you did in exam. This is RE is equal to 1 kilo ohm and beta is equal to 120. Okay, all right. So this is the problem. So you need to find out SVBE. So let's write down the objective. Okay, objective of this problem is to find SVBE and delta IC for the three circuits: emitter bias, fixed bias, and voltage divider bias for T1 is equal to 25 degree and T2 is equal to 100 degrees Celsius. So when the temperature is changing from 25 to 100 degrees Celsius, what happens to SVBE and delta IC value? All right. All right. So first, let us find out delta VBE, change in base emitter voltage. So delta VBE is equal to VBE, okay, at a later temperature minus VBE at the initial temperature. Okay, and that is 0.48 minus 0.65. Okay, it gives minus 0.17 volts. So we have found delta VBE. All right. Now let us go to the fixed bias circuit. Fixed bias circuit. Now, in case of fixed bias circuit, we have found that SVBE is equal to minus beta divided by RP. Minus beta divided by RP. Okay, this you have to solve it. Okay, you have to find it. We have done it for voltage divider bias. So similarly, you could do it for fixed bias circuit. So SVBE for a fixed bias circuit is minus beta divided by RP. So that is minus 120 because beta is given as 120. Okay, divided by RB. Okay, what is RB? 270 kilo. Okay. So that gives the value as minus 0.44 into 10 to the power minus 3. Okay. Fine. Now, How do you find? So SVBE you have found. Okay, how do you find delta IC? Okay, remember one thing. What is the definition of SVBE? So SVBE is defined as change in collector current due to the changes in base emitter voltage. Okay, so that implies your delta IC or change in collector current IC can be found simply by multiplying the stability factor with change in VBE. Okay, so this is the formula which we use to determine the delta IC. Okay, so what is it? SVBE we have already found, minus 0.44 into 10 to the power minus 3 into delta VBE. Delta VBE was, I mean, we found the value, right? We have already found. So it is negative 0.17. So, sorry. So when you multiply the two negative numbers, you will get delta IC is equal to 74.8 microamperes. All right. So that is for fixed bias. Once fixed bias is done, you can go for voltage, emitter bias. Let's go in sequence. Emitter bias. Now, in case of emitter bias, okay, SVB is minus beta divided by RB plus 1 plus beta times RB. You see, you don't have to by heart. In fixed bias, there is no emitter resistor, hence there is no RE. In emitter bias, there is emitter resistor, hence, you will have the reflection of emitter resistor in the input side. So that's the reason 1 plus beta has come into picture. Okay, so that is equal to minus 120 divided by RB. So for emitter bias, RB is 39 kilo ohm. Okay, so it is 39K plus 121, because 1 plus 120 is 121 into RE. RE is 1.2 kilo ohm. Okay, so I have already calculated the value. So yes, VB, you will get it as minus 0.65 into 10 to the power minus 3. Okay, so having known SVB will enable you to find the stability, the change in collector current IC, that is SVBE into delta VBE as discussed in the previous case. So minus 0.65 milli into minus 0.17. So delta IC, you will get it as 110 microamperes. 110 microamperes. Okay, so that's the change in collector current. And finally, you can do it for voltage divider bias. Okay, if you know emitter bias formula, you can write it for voltage divider bias circuit. Okay, so yes, VBE for a voltage divider bias circuit is minus beta divided by, in place of RB, you have RTH, the Thevenin's resistance. Okay, and then rest all remains the same. RB, okay, where RTH is R1 parallel with R2. So that's 39 kilo ohm parallel with 10 kilo ohm. Okay, so that you will get it as 7.95 kilo ohm. Okay, please check my calculations. Okay, so your SVB becomes minus 120 divided by 7.95 kilo plus 121 times 1 kilo. So SVBE will be minus 0.93 milli. Okay, that's okay. Or I would write 10 to the power minus 3. Okay, so therefore, delta IC is SVBE into delta VBE. Okay, and that is equal to minus 0.93 milli into minus 0.17 volts. So delta IC, you will get it as 158.1 microamperes. Okay, so that's your delta IC. Okay, so this is how you solve the stability problems. Okay.